If you drop a plugged-in appliance into a bathtub, the results are famously lethal. Yet, if you were to fill that exact same tub with pure, perfectly distilled water, dropping in that same appliance wouldn't cause a shock at all. The water itself isn't the danger. The shock is actually carried by the hidden chemical impurities naturally dissolved in everyday tap water. This dynamic, where chemical energy converts into electrical energy and vice versa, is the focus of a scientific field called electrochemistry. To make electricity flow through a liquid, you need specific agents called electrolytes. When these substances dissolve in water, they snap apart into distinct positively and negatively charged particles known as ions. This source document categorizes these electrolytes based on their strength. Strong electrolytes, like table salt, completely dissociate in water to provide many ion carriers. Weak electrolytes, like vinegar, only partially dissociate, which results in a much lower concentration of carriers. Recognizing these invisible ion carriers is the necessary first step to controlling liquid electricity, a concept that allows us to engineer modern power sources like lithium-ion batteries. This flow of charge is known as electrolytic conduction. But unlike electrons moving through the solid lattice of a copper wire, ions must physically swim through a dense liquid environment. Because they have to muscle their way through the fluid, this environment acts like an obstacle course governed by 5 distinct physical factors. Returning to our source text, we see the first 2 factors. The nature of the electrolyte determines how many ions are available, and the nature of the solvent matters because polar solvents are effective at pulling those ions apart to generate flow. The third factor is viscosity. A thicker liquid, where the solvent molecules interact heavily with each other, creates physical drag. This slows down the swimming ions and lowers the overall electrical conduction. The physical thickness and polarity of the surrounding fluid dictate whether the power can actually travel, making the liquid environment as critical as the chemicals added to it. The fourth factor is temperature. When you apply heat to the system, you increase the degree of dissociation and cause the ions to move more rapidly, directly increasing the liquid's conductivity. Finally, we have the fifth factor listed at the bottom of this page, the concentration of the solution. This variable behaves in a counterintuitive way compared to standard logic. It is easy to assume that because ions carry the charge, adding a higher concentration of electrolytes will automatically equal more electrical conduction. However, as concentration gets too high, conduction actually drops. The ions become overcrowded, physically blocking each other from moving through the fluid. Diluting the liquid increases conduction by giving the existing ions the physical space they need to travel freely without colliding. Engineering an ideal liquid conductor involves balancing energy and physical space, as overloading the solution with chemicals creates a bottleneck for the current. While understanding the physical flow of ions is essential, engineering reliable technology requires translating those physical movements into precise mathematical values. This document outlines how we calculate the pushback those ions face, known as resistance. Grounded in Ohm's law, resistance is determined by dividing the potential difference across the conductor by the current flowing through it. Because liquid volumes can vary, scientists standardize this measurement using specific resistance or resistivity. This is calculated by multiplying the resistance by the area of cross-section and dividing by the length. Resistivity measures the resistance within a specific volume, exactly 1 centimeter in length and 1 square centimeter in cross-sectional area. By pinning down this exact mathematical resistance in a standardized volume, engineers can accurately predict the electrical output of any chemical battery. To finalize the calculation, engineers move from measuring the obstruction of the current to measuring its passage, or conductance. As shown at the top of this page, conductance is defined as the mathematical reciprocal of resistance. It is expressed through 3 units of measurement: the inverse ohm, the mho, which is ohm spelled backward, or the official SI unit, the Siemens. Manipulating physical variables to maximize these Siemens is how the tech industry optimizes lithium-ion power grids. By mastering the mechanics of liquid flow, science has taken the scenario of a bathtub shock and engineered it into a safe, measurable engine for modern portable technology.